Hi there everyone, and welcome to another Touch Designer tutorial. Today's tutorial is going to expand on this earlier network we built very early on using POPs, which creates an attractor effect where points pull towards an attraction point. And what we're going to do is, using the field pop and some GLSL, we're going to make a network that allows us to have multiple attractors very easily set up in one network. The core mechanic of what we're going to do today is going to look something like this. This is just a debug kind of behind the scenes view, which I'll show you later. But the core mechanic is going to look something like this. We can obviously use any point file that we like. In this case, I'm just using a point generator pop. And as we can see here, there are lots and lots of attractors kind of doing their thing and buzzing around. These two files will be available as a project file on my Patreon in the Patcher tier. And component level subscribers will get something that's a little bit more built out. Essentially a drag and drop tox that can be used on any point cloud. You can drop it into a project and apply multiple attractors really easily. I'll also include an example file of how I work with 3D scans using this type of effect. Before we start building the main network, I want to do a quick recap over the field pop. The field pop allows us to take an input, whether that's a geometry or a point cloud, and basically applies a weight attribute to that input. What we can see is that we have an output page and we're outputting this weight attribute. In this little example here, what we can see is that as I move this transition, we're changing the amount that the weight is applied to each point in our point cloud based on a number of parameters, such as proximity. So as I change this range, we can see that fewer particles will be white or blue based on how this range is being applied. Likewise, with transition align, we can change how this weight and distance is being applied to the point cloud. If we go to the transform tab and make some transformations, we can also see that the network is responding to these changes in position. So we can see that that weight attribute is being changed for each point in our point cloud. So this is great, and this is what we built our attractor logic around when we had our single attractor, because essentially we have a weight value for each of our points, which allows us to see if an attractor is near to that point and then perform a push or pull operation. But what we want to do is create something that has multiple attractors. And something that is really cool about the field pop is we can actually pass in a second pop with positions. And what this means is that we can control, using a secondary pop, the weight attributes of multiple points. And we can apply that using this spec pop reference here. We can see that that reference has been hooked up. We can also see that I've made a bit of a change here, where I've added in a mathmix attribute to change our position attributes to t attributes. So t, x, y, z, or t, 0, 1, and 2. Don't worry, we'll look at doing this later as we build our fuller network. And when this is applied, we can see that the translate is grayed out in the field. I can then utilize these multiple points and either apply them using a mathmix. I'm just doing a very simple a times b operation here, or I can use my weight parameter to essentially delete points out of my system. And we can see here I've merged them back together, so we essentially have a globular center that is surrounded by the static geometry that's just being deleted. So this is the extra mechanic of the field pop that we're going to use today to allow us to have multiple attractors. Now we understand a bit more about how the field pop works, let's get started with the main network. We're going to create a point generator. This could be replaced by whatever point cloud you're looking to manipulate, but for simplicity, I'm just going to use the built-in point generator right now. I'm going to drag that out to a null, which will be the end of our chain, and I'm going to add in a field pop. Now, the next thing I want to do is I want to create another point generator. I'm going to go into the number of points and I'm going to set it to something kind of small, about 5. And this is going to be the number of attractors that we're going to have in our system. So we'll just have 5 for the time being. I'll bring this out into a null. And I'm going to call this attractor pos. And now what I can do is drag this onto the spec field of the field pop. And now this is linked with that attractor position. What we want to do from this point is we actually want to get the attractor position so it's actually accessing this translate parameter here. We can see that this hasn't quite happened yet as the translate parameter is still visible. What we want to do is add in an attribute that changes the P position value to an attribute called T. So essentially we have Tx, Ty, and Tz, or T0, T1, and T2. To do that, I'm going to make a math mix pop. And under the combine tab for operation, I'm going to select A. I'm going to select P for the position parameter. And in the result scope, I'm going to call it T. So now, if we go back to our translate, we'll see that this has been grayed out, which is fantastic. The next thing we can do to just check that this has actually worked is add in a delete. And I'm going to go into attribute. I'm going to select weight. Let's move this to that. And also in the field pop under our transition range, I will move this. If I turn down my radius, we should see that we now have multiple positions that are being accessed in our delete. We can basically just choose whether we're doing larger or smaller than. All we're doing here is just a little check to see that each one of these points is actually doing something in our weight attribute. What I can also do here is add an animated component. So between my point gen and my math mix, I'm going to add in a noise. I'll set my amplitude to 1. And on the transform tab, I'll say abs time dot seconds times 0.1. So now these are moving around, and we should see that our delete here is deleting chunks and moving them around. So this is actually responding exactly how we want right now. And so this is great. I'm going to move this down and just plug this in here. We can keep this as a useful little view if we want, or we can just bypass it. I'm going to bypass it right now. Okay, so here we go. We have our attractor positions feeding into our field, and now we're going to work out a way of using them. The first thing I'm going to do is I want to just take a look at all the attributes we have access to. So we can see here we have a singular weight value, and this is kind of an aggregated weight value, and we can just access one versus a weight value for each point in our attractor array. So this is not very useful to us right now. To reveal the weights for each of the individual attractors, I'm going to go onto the field pop, and under output, I'm going to say per field weights on. And so that's going to be called weights. We should now see that we have all these additional weights that have been made available. These are weights specific to each of the attractors that we have in our system. And what we'll see if I make, say, 20 attractors, we're going to expand the number of weights that we have. So basically, we're going to have an individualized weight for each attractor. And this is what we're going to use in our GLSL component. Now, there may be a way of accessing these weights without using GLSL, but for me, this makes the most sense. So between this field and the null, which is the end of our chain, I'm going to add in a GLSL pop. We can see here that we have our compute shader, which is what we're going to be working in today. And we also have this handy info. I'm going to split my screen. I'm going to do text ports and DATs, which you can bring up from this drop down, or you can also do Alt-9, and it's going to bring up a text editor that we can work with. To see the compute shader in this section, I'm going to right click and say edit contents in text port. I'm also going to right click on this GLSL1 info, and I'm going to say view contents in text port. So now we have these two tabs to toggle between, and here we can write code, and here we can see if it's compiled successfully or if we have any issues that we need to address. Okay, so now we're going to write a little bit of GLSL. Basically, what we're trying to do is access all of these weights individually and apply that into our attractor system. So we're going to use very similar logic to what we used when we built our initial attractor, but we're applying this in GLSL context to lots of attractors versus doing it all in our math mixers. So this is going to give us a lot more control over all the individual attractors. In terms of what we'll see when we look at the starter code in this compute shader, we're going to see this main function, and we're also going to see this commented out line of code, which is basically showing us how you would access an attribute within the shader itself. So in this case, this is looking at the position attribute and accessing that. It's also giving you an alternative way of accessing the same bit of information. We also have a few things that are built in that we don't want to touch. For example, this const_u_int_id is going to give us the ID index for each of the particles that we're looping through. The main thing we have to do here is sort of consolidate all the particles here with these attractor positions here. And in this case, we have to do something that's sort of akin to a nested loop, where each of these individual points is going to be checked against all of these points. So in this case, we have 20 attractors. Each of those attractors is going to be checked on all of the 10,000 points that we are generating in our input. And this is partly why GLSL comes in really handy here. I'm also going to bring up this little diagram of the sort of steps that we're going to use in kind of mathematical terms to create this attractor, just so I have this visible to me. And I'll make this kind of small over here. I'm going to start off by deleting this line of code, and I'm going to make some room at the top for adding in uniforms. So uniforms are values that we can pipe in from this area of our pop. We can, under the vectors tab, write in the names of these uniforms and actually pass those values into our code, which is going to be really useful. I'm going to start out by creating a uniform float, and I'm going to call it FA for force amount. And let's just label this as we go to make this accessible later. I also want a uniform float for fall off. This is the fall off factor. And something that's important here is obviously just making sure you use the right data type for what you need, whether that's a float or an int or a vector. This will maybe make more sense later, but as you're working this together, it's just important to keep an eye on the data types you're using. We're going to create a radius, which is going to be the radius for our attractors. So I'll say uniform float max radius of each attractor. We're also going to have an option to do some normalization. So uniform int, because this is essentially going to be a sort of a toggle, and I'll say normalize sum, and this is going to be toggled between 1 and 0. So if 1 will normalize our direction, and if 0 will use the raw sum. and then we're going to do a const float, which we're casting as a const. So this will just be constant throughout the whole code. And we're going to call it EPS. And we're going to give it a really, really tiny value. And this is basically so we can avoid 0 divisions. You don't necessarily need this, but I'm going to have it in just so it helps. Okay, so these are all the uniforms that we're going to use. And I can start out just by adding these in. So I'll put in FA, fall off, max radius, and it's important that all this stuff is copied correctly, and normalize sum. This one can be switched to an int, and that can be switched between 1 and 0. We'll play around with these values later when we start getting something that works. So this is a great start. Now we actually are going to write the code that's going to allow us to make these changes. We'll start off with a vec3 for our position, and we want to access this with td in, and important here that the n is lowercase while td and I are all uppercase, underscore p, capital P, because we're going to access the parameter p. It can be useful to just keep an eye on all of these parameters that are available. It's important that we make sure that we're accessing attributes that actually exist. And to make sure that we know what attributes we actually have, we can refer to this pop21, and we can look at this drop down, or we can actually go onto our various elements and we can see that our attributes are labeled here. So we have our position and normal, and here we have our weight and weights, and our weights are showing an array of 20. So that's 20 different separate weights linked to the number of particles we've selected. So I know that P is an attribute that I want to access. I'm going to do 0 ID. So this means I'm going to loop through all of my particles. And it's important to make sure we're adding semicolons to the end of all of these clauses. So let's just say particle pos from first input. And yes, we can put multiple inputs into this GLSL pop. The next thing we want to do is we're going to create another vec3, and we're going to call this force. And this is going to be a holder for the force values that we're going to be calculating for each of our weights. So it's a capital F vec3, and we're just going to put 0 here. So right now, each of our values in our vec3, the x, y, and z value are all going to be 0, 0, 0. And that's fine. We'll create a float, and we'll call it total W. And again, we'll give it a value of 0, floating point. And so this is going to be our accumulator for total weights. And basically what we're doing is we're putting together a piece of code that's going to allow us to do this step by step on each attractor for every point, which is going to give us the desired effect. We're now going to start writing some code to bring in the attraction points. So right now we see that we also have this attractor position, and I'm going to make sure to bring this in to my GLSL 1. I might actually just turn off the background display so we can see here. So I have my attractor position moving into my GLSL 1 as well as the field input. So to access these, I'm going to create a uint. I'm going to call this NA for number of attractors, very catchy, I know. And I'm going to say equals. And what we want to do is we want to access this second inlet. And so to do that, I'm going to say td input. And so it's important here that tdi capital, the nput, all lowercase. We're going to do num for num points. and this reads as TDI, or cap, input num points. So it's important that we have these capitalized, the N and the P capitalized, and then we're going to access that 1 equals number of attractors. So this will be the number of attractors that we're going to loop through. Now this gets to the good part. So let's loop through all of the attractors. And to do that, we're going to create a for loop. And for this, we're going to say for, and then we're going to open up a bracket, uint j equals 0, j2, number of attractors, na, plus plus j. We're going to close the bracket and open a curly bracket. And this is going to be where we write our attractor loop. And this is where all that math stuff is going to happen. So I'm just going to actually split this and view this just as a little piece of text that I can refer to help me with the step-by-step of what types of vector math I have to actually apply. The first thing we want to do is access the attractor position. I'm going to make a new vec3, and we're using vec3s here because all of the position attributes have x, y, z parameters. And so I'm going to make a vec3. I'm going to call it a pos, and this is my attractor position. And for this, it's going to be equals td in underscore p. And like we did before, this is accessing the 0 index of our input, so the index of each of the particles from this field. And here what we want to do is say 1, comma, j. And what's happening here is we're just looping through the attractor positions with the ID of j. If we looped through all the attractor positions with this index, it's going to go way over, right? Because here we have 10,000 particles versus 20. So this is to make sure we're only looping over the attractors that we actually have, and we're not going to run into any issues there. The next thing we need to do is create a vector that's going to calculate our distance, the distance from the particle to the attractor. So we're going to create another vec3, and we're going to call it d for distance. And what we want to do here is a subtraction. So apos minus pos. And this is going to be our distance vector that we're starting with. I'm commenting this as we go along, so it kind of gives us a bit of an understanding of what's happening when we look back over the code. And so this is that first section here, right, where we're computing the direction. Then what we want to do is we want to calculate distance in some way. We're going to do a little bit more fancy things here, but essentially that's what we're going to do. So I'm going to do float r2 equals the dot product of dot open brackets d comma d plus EPS. And this is going to be our squared distance, and just adding that EPS to avoid 0. So that kind of just makes sure we don't ever have a 0 division. So we have our squared distance there, and now we're going to create another float. We're going to call it r, and we're going to say equals square root of r2. Close that up, and that's going to be our final distance that we're working with. Then we can create our direction, so we're going to call it dir equals d divided by r, and so this is really our normalized direction to the attractor. We can also add in a weight attribute, and so we'll keep this as a default weight right now, and so we'll just say float w equals 1.0. And now we're going to create a fall off, so I'll say float f equals fall off bigger than 0. This is a little expression here, all in one line, and question mark how open bracket r minus fall off colon here 1.0 semicolon. And then we can apply that to this vec3 for force. So we can then say F plus equals direction times W times F, close brackets, and end line. And then total W plus equals W. And this is the end of this loop section here. And now we have to just put this as an output. So to do that, I'm going to write force, which is the name of the attribute that we're going to be modifying in our GLSL. And I'll talk about that in a minute. Open brackets ID. The ID relates to what we're looping through here. And I'm going to say equals F times FA, so force amount. So we're going to output our force times the uniform of force amount so we can control the intensity of that force. And now we should have something that works, although we'll probably have a few bugs to fix. We can already see something happening here. So we can see here that in force we have undeclared identifier, no code generated, but that's pretty good because we're right on 46. And of course the error that we have is in this GLSL here, we're looking for a parameter output to alter. And so we can see here in this output attributes, we actually don't have a force that we can alter. And what I'm going to do here to create that force attribute that can be altered and written to is between the field, just going to free up some more space, is between the field and the GLSL, I'm going to add in an attribute. And let's just take a look. Force should be a vec3. So yeah, we want a vec3 for force. So under custom, I'm going to create an attribute called force, and I'm going to make it into a vec3. And now I should be able to add that into my output attributes, and we no longer get an error. Okay, so let's just take a quick look to see if this is working and that we actually have a force attribute outputting. Okay, force is there. And force is moving, which is great. We're just not applying any of that force to these particles right now. And we could modify the GLSL, but what I'm actually going to do is I'm going to apply this in a separate math mix just to give us a bit of control at the end of our chain. So I'm going to create a math mix. In the combine tab, I'm going to say A plus B. I'm going to say P plus force. And now we can see that things are starting to move for us. Let's bring this out into a geo and then visualize it. Okay. And what I'm going to now do is just tweak some of these vector controls. So we can see here, if I change my fall off, we'll see that we create different types of effects. Maybe 0.01 is too small, but that's okay. Fall off, we can scale down, or we could even scale up. So if we have a higher fall off, we're going to have a more dramatic kind of attractor. The max radius, we haven't applied that right now, and also the normalized sum. This is partly because I'm simplifying this from a longer piece of code that allows you to actually add in weighted values so that you can have attractors of different sizes and different weights. In the interest of not making this tutorial super long, I'm not going to include that additional bit of code in this tutorial, but it will be available in the component tier of the Patreon alongside a little video that I'll make where I implement that. But what we have at this point is we have attractors that we can actually place in space and have multiple applying to our point system. We can obviously create more dramatic effects if we go in and start playing with some of these values. So we can create things that are really doing some interesting stuff. Minus values are going to push away versus positive values which are going to pull towards. And so this is something that you can obviously spend lots and lots of time playing with. Now, there's one more thing I'm going to suggest we do to this system, which is going to make it a little bit more dynamic. And that, as always, is we're going to add in a feedback loop. So I'm going to place a feedback after my attribute and before the field. And I'm going to drag that null onto my feedback loop. And now you can see we have this really chaotic sort of strange attractor style thing. And this is because the attraction will keep pulling in every frame. Or if we switch it around, pushing out. And what I want to do here is I want to have first a reset for my feedback loop. Dragged onto that start. So this is going to be a keyboard in reset. So every time I press that keyboard, it's going to start from scratch. And that in itself is kind of a cool effect. But I don't actually want this to just keep growing. I want to mix in some of the feedback with the original signal. So into the math mix, I'm going to take the attribute value. I'll create a new operation. I'm going to say mix ABC, I'll say P, in 1P, and then I'll give it a value of like 0.3. And then we can tweak how much feeding back we're doing. So if it's at 1, it's going to be really boring and not doing much at all. If it's at 0, it's going to be doing that whole growth thing. And if it's at something like 0.1, it's going to be taking a little bit of both. So you can kind of control the amount of feedback that you're applying here. So in between this GLSL and this math mix, we could also apply some things like, for example, we could put in a noise if we wanted to add in a bit of extra texture, although that's actually the other layer. But either or, you can add in some noise that can control that system. And you could also play around with turning this GLSL, just tweaking these values slightly. So you've got your force amount and you've also got your fall off. So let's try a smaller value for the fall off and a bigger value for the force amount. Let's see. And we'll do an attract to versus a push away. Maybe a bigger fall off, or even a smaller fall off. It's all just tweaking values at this point. You can obviously add in other types of geometries to effect. So let's just switch this to a box. We'll have to repulse that feedback. And there we go. If I say wanted to bring in a point cloud, I can do that. This is a little point cloud of me. And I'm going to bring that in and just connect that into my attribute. We can see that something is happening. Look at me getting all rotund. And I press 1 and the color should be added to it, although it may crash my system. There we go. I might need to reduce some of the points there. But this is essentially how easy it is to just drag and drop. There may be some optimizations I could make here. Now, if that seems like a lot to handle, don't worry. I have a handy GLSL attractor tox, which you can drag and drop into your projects. Let's bring back that point cloud and connect it up into the first inlet and output. We can see that this is much more optimized. If we go inside the network itself, we'll see that it's very similar with a few extra attributes that we can control. I haven't built a outside UI for this yet, so you do have to go in currently to the system itself. So we can control the number of points that we're creating and always reset that feedback. So 5, kind of small. Let's do 20. We can set things like the noise, which is controlling those points. So basically that's what's driving their movement. So this is all just that input. And we also have a special weight factor here as well. So if I turn this up, we'll see that the attractors are much bigger in terms of what they're pushing and pulling away, versus if I turn this down, where we can see basically there are no attractors. So this is an extra weight-based value that's been set up to add some control to this system. The weight-based value also means that we're accessing values that are above and below 1, so we get automatically a sort of a more random push and pull. So some attractors pull towards themselves while others push away. In the GLSL, we can tweak the force, which is called SD here. We can tweak that max radius, so have things much bigger. That's also implemented. And also turn down this normal sum, which just gives you the aggregate, which isn't so cool. So generally keep that at 1. Likewise, we have a noise that you can play around with at the end of the chain. And we can work with the math mix at the end of the chain as well. And I should probably annotate this in terms of how much we're actually mixing between the two systems. So if I do that at like 0.1, it's going to be a much crazier system. Let's turn these things down as well. But this is essentially a sort of a drag and drop component that you can use in your projects. If the following of the GLSL component part was a bit much to follow, this is available in the component level tier of my Patreon. I think that's all I have on GLSL attractors for today. Thank you so much for watching, and stay tuned for more tutorials soon.